this is lesson 47 for 7th grade, and today's topic is powers of 10. As always, we've dealt with powers of 10 before and in the past, but now we're going to come up with some specific rules for powers of 10 and see what that kind of does to our decimal and what we can do when we're multiplying things by the same base. So first we're going to start with some tens. Alright. It says here to start off, the positive powers of 10 are easy to write. The exponent matches the number of zeros in the product. So for instance, 10 to the second power means 10 times 10, and 10 times 10 is 100. Or we could have seen that we were going to have two zeros here. Same if we look at 10 to the third power. 10 times 10 times 10 equals 1,000, 1 with 3 zeros. And here we should have 4 zeros, 10,000. Okay? And tomorrow we'll have the students read through a couple things, and we're going to have some exponent rules. When we multiply numbers with the same base, divide numbers with the same base, and take powers of powers of the same base. So we'll have them read through some examples and things like that, and then we'll come back together and go through those things. But here's some things we should find out. Now this table is going to look a little funky. What this basically means, if we have a number A, or basically same base, we've got exponents to those bases. So let's just make one up here. 2, let's say 2 to the third times 2 to the fourth. Okay, here our base is A, so that would be 2 over here, and x is an exponent, 3, y is an exponent, 4. What this says we can do is we can just add those two exponents together with the same base. As long as these bases are the same. It only works if the bases are the same that we can do this. So this equals 2 to the 3 plus 4, which equals 2 to the 7. So that's a rule that we have, and the reason that this works out is because, let's think about what this actually means. 2 to the third is 2 times 2 times 2. So that's 2 to the third. 2 to the fourth is 2 times 2 times 2 times 2. And all of this is being multiplied together, and we actually have 1, 2, 3, 4, 5, 6, 7 2s. And that's why this rule works. So we should get 2 to the 7th there. Okay? So whenever your bases are the same and you're multiplying, you can add the exponents together. So that's addition. X plus y or a. Looks kind of funky there, but we can add when we multiply. I'm not going to try to copy that. Where did my eraser go? There it is. Alright. Okay, same thing goes for when we divide. If we have the same base over the same base, we can actually subtract our exponents. So let's take a look at one of those. Let's say we have 2, well, let's go 5 to the 5th, all over 5 to the 2nd. This says our shortcut is we can do the top exponent minus the bottom exponent. So this equals, and we can do this again because we have the same base, 5 and 5. 5 to the 5 minus 2, which equals 5 to the third. Okay? So we got this up here, and we've got this down here for that one. Okay, longhand, this means, what do we have on top? 5 5s. 5 times 5 times 5 times 5 times 5, all over 5 times 5. And if we do some canceling, these are being multiplied, everything up here is being multiplied, which means we can just do this, and you're left with 3 5s, 5 to the third power. And that's why that rule works. Lastly, we have a to the x to the y power, okay? So this is, let's just go 3 squared to the third. What this says is we can multiply these two exponents together. So we get 3 to the 2 times 3, which equals 3 to the 6th. Now let's see why this works. This means we have 3 of whatever is in here, so that's 3 to the second times 3 to the second times 3 to the second. Okay? Now, same base, which means we could actually use this rule up here. We're multiplying all these now. 2 plus 2 plus 2 is 6. Well, let's say we didn't notice that. Well, 3 to the second means 3 times 3. We have another 3 to the second, 3 times 3. Another 3 to the second, 3 times 3. How many 6's do you have? 1, 2, 3, 4, 5, 6. That's why that rule works. So those are those rules, examples of those rules. And we're going to go over another example here next, where we have to fill in the blank. Okay? So, letter A here, we have 2 to the 4th times 2 to the 2nd. We are multiplying, so we're going to follow this rule here, which means we can add our exponents together. We do have the same base, 2 and 2, so this works, and we can do the adding. 4 plus 2 is 6. Okay? Letter B, check and see if we have the same base. We do. 2 and 2 again. This one says we can do 4 minus 2, or x minus y, whatever our exponents are. Whenever we divide, we have the same base, we can subtract. 4 minus 2 is 2. So 2 to the 6th, 2 to the 2nd, and C, that's this situation, 2 to the 4th power, 2 to the 2nd power, we can multiply our two exponents. So 4 times 2 is 8. That's how we would fill in our blanks there. So just to make this clear, we couldn't do this we couldn't add 5 and 2 together here because 2 is a different base than 3. It only works if your bases are the same, okay? So here we'd actually have to go through and multiply this out separately because once again we can't add those exponents together because the bases aren't the same. So we would have to figure out what 2 to the 5th is, which is 32, and then multiply it by 3 to the 2nd, which is 9. So 32 times 9 is how you would get a final answer there. But we can't add them together or do anything with the exponents unless we have the same base. Okay, moving on here. We can use powers of 10 to show place value as we see in the chart below. Notice that 10 to the 0 power equals 1. Okay? 10 to the 0 power is 1. Actually, anything to the 0 power is going to be 1. And I will prove that in class probably tomorrow. But for now, let's just know that anything to the 0 power is 1. Okay. So we're going to look at this example here. We can use powers of 10 to write things in expanded notation using powers of 10. And we're going to go ahead and do this one. Just want to make sure I have it in the right format that they want. So, oops, a little too far. Yep, okay. So we will be good here. Okay. So we look at what place value each number is in here. 5 is in the thousands place. 1,000th place. So we're going to use 5 times 10 to the 3rd. And we're going to add 2 is in the hundreds place. That's 10 to the second plus 2 times 10 to the second. We're going to add to that. We don't have to do anything with 0 because that's by itself. Oh, it's 0, so we don't need to factor it in. 6 is in the ones place. So it'll be 6 times 10 to 0. So that would be our expanded notation for that number. 5,206. If we went through and calculated all this, we would get this number. That's just to show the place value of each number. Okay, we're going to try this here. When we multiply a decimal number by a power of 10, the answer has the same digits in the same order, only their place values are changed. So, if we multiply by 10 to the second, we look at this right here, and all we have to do, if we multiply this by 10 to the second, is move the decimal over 2 spots to the right. So this is actually 4,623.5. So that's what we'll do when we multiply by powers of 10. Pretty easy. We're going to use that with scientific notation once we get to it. The opposite happens when we divide by powers of 10. For instance, if we take 4.75 divided by 10 to the third, we still move our decimal 3 places, but we go 3 places to the left instead. So let's take a look at this one quick. Make sure my time is good. We're going to take 3.5 divided by 10 to the fourth. So we're going to move the decimal 4 spots. We're going to go to the left. It's right here, so we're going to go 1, 2, 3, 4. Put our decimal there. Fill in our loops. 1, 0, 3 zeros. So our answer would be 0.00035. And that's how we would use our powers of 10 to multiply or divide. That's basically all I have for today. So we'll talk more about this tomorrow. We'll see you then.